Let's try it. And I found it, and it's done. Now see, that is much faster. We didn't have to go through the entire board. Welcome back to Arcade. I am Super Tommy, and in this video we're going to look at BreadthFirst Search algorithm. So in games, BreadthFirst Search can be used to find the shortest path, or at least one path, from wherever a player character is to a target location. So BreadthFirst Search, usually when you go look at it, is described in trees or graphs. So now trees is not that useful for us in games, but a graph is. So a tile-based game would be sort of like this. We have this map here, let's say, it's just a set of grids. I think this is 8 by 8. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. So it's 9 by 9. Got a 9 by 9 grid here. The black squares are walls, and then the white squares are places you can actually move to. And this red square is the starting position for the player. And so what we're going to do in this video is implement BreadthFirst Search and then generate a path that you can use to go from where the player is to where the player should go. Now, usually, maybe don't use it for the player, but for like AI or some other non-playable characters or enemies that are going to move to a certain location. So let's look at the BreadthFirst Search Pseudo Code. So let's see. This is just a Wikipedia page. You can look through it. There's also DepthFirst Search, which the difference being in depth, you'll go down one path all the way. In BreadthFirst, you would go hit all the children from the starting node, and then all the children from the level that you're at. That was under. And instead of going down and doing everything in one path first. So let's see, here's some pseudocode. All right, so here's the pseudocode. And this is not exactly descriptive. So we've actually translated it into what you're actually going to need here in this generate path function. So a lot of this code here that you see right here is just setting up our grid. This grid that you see here. And then when we click on one of these squares, these tiles, we're going to reset the grid, which is simply going to make the starting position red and then the non-walls white, because we're going to change colors so that you can see the path and how the algorithm works as it expands out and figures out what path to use. So that's reset grid, and then we have generate path. So that's what we're going to implement, the generate path function. So here is how we're denoting where start is, which we set as 2 in our grid setup. All right, so let's get started, and here is our translated version of the pseudocode. So what we're going to do, I'm going to take a queue, and in this queue, a first in, first out queue, we're going to, while the queue is not empty, we're going to take the first element out of the queue, get the neighbors, and then for each neighbor, if it has not already been discovered, we're going to mark it as discovered and then add that neighbor to the queue. And then we're going to do that until the queue is empty. And then after we have all that information, we're going to generate the path based on the connecting cells. And then we're going to just draw that path for you by coloring each square on the path orange. All right, so let's just implement it and you can get a better sense of what we're doing here. So first, let's make a queue. We're just going to leave these instructions here. So we're going to use a queue, we'll call this queue, which is just a list in JavaScript. There is no queue data structure that I believe natively, but the JavaScript array works perfectly fine as a queue. So what we're going to do is we're going to put the starting position into the queue so that when we start, it will in fact be not empty. So queue.push, and what we're going to push is not the cell here. We're going to push the actual row and column values of the starting position, which we have set here. Right, start position is the row and column of the starting position. So push start position. Now, while queue.length greater than 0. So while it is not empty, which means it is greater than 0, we are going to dequeue the first one. Actually, so row column, so this is the first row column we're going to use, q dot shift. Shift removes first element, yep. So in a queue data structure, you would have enqueue for adding to the queue and dequeue for taking off the queue. But in JavaScript's array, there is push, and then you can pop for a stack or a shift if using it more like a queue. Okay, so that's row column. Now we're going to get the neighbors of this starting position, or whatever this current position that we're using. So let's just, if we're starting, it'll be here. The neighbor is going to be top, left, right, and bottom. So let's just do this neighbors, and it's going to be a list. So row, so let's do top, which is going to be row -1, and then the same column. And then let's do right, which is the same row, and then column will be column +1. And then let's do bottom, and then that's row +1, same column, and then we're going to do left, which is row, and then column is column -1. So rows are these, right? Each horizontal row is the row. So we're going to go up one, that's row -1. If we're at this row, just 4, want the top, which is the third row, and the same column. So that's how we derive these values. So now we have the neighbors. Next step, for each neighbor. So let's just do a for loop here. I less than neighbors dot length. Okay. All right, let's see. So now we need to know if a neighbor has been discovered or not. And because we're using this to find path, when we're going to consider what is discovered as in what exists in a lookup table that we're going to make, that we'll use to look up the parent of the current neighbor cell that we're looking at. So for example, let's say we're going through this neighbor, and this is the start. So the first one is top. So we're going through here. The first neighbor is this one, the top neighbor, and we want to see who its parent is. Now its parent is start, right? So that's its parent. And so if we've noted who a cell's parent is, it's also considered discovered, that we've already processed that node. And then we're going to use this parent data later to figure out the path by working backwards from the target to start by going backwards through all the parents. So let's here make another, we're going to make a hash map. We're going to call it parent for cell, right? Just an object in JavaScript. And we're going to need to key it by something. So we're going to key it by the row column string. So let's see here. So neighbor, so let's do this. Let's call n row will be neighbors I dot row. So n row stands for neighbor row, and then n call neighbors I dot column. Call. Okay, so now we have that. Let's say we make a key. So this key is going to be row neighbor row by neighbor column. So we're using string interpolation, which is a shortcut for doing effectively this, plus x plus n column, right? So you could also do this, right, like this. That would be the same as right here. But we prefer this, or at least I prefer this syntax since it's a little bit easier to read. Okay, so now we have the key. So now what we're going to do is check if key in parent for cell. Right, so if it's already in there, then we've already processed this cell, and we can continue and skip it. Otherwise, we are going to mark as discovered, okay, which means parent for cell key Now we're going to have to give it some information, including when we go back and look in this the parent and actually the key of the parent so that we can look it up. So here what we're going to do is key. This has to be the parent's key. So if you're up here on top, the parent's key is not going to be this key here, right? The parent's key is actually row column. So let's do current key, and that is row by column. Okay, so that's current key, and then I'm going to do cell. Cell is this guy, so we only have this row column right now, so let's go here, current, and then we have the cells. We have the cells 2D array, which is right here. And then we populate this 2D array here when we go through the grids to create these cells. And so we push it right here. So that's the setup. So effectively the cells 2D array matches this rows, this grid 2D array. Instead of having 1, 0, and 2 in it, it will have actual rectangle instances that we can use to color, like color these actual squares, visible squares. So it mirrors the grid 2D array exactly. So that's current, so cell current. All right, so now we have marked that. So now we want to push onto the queue the neighbor. And so now neighbor's I, that gives us that. So what we want, what was in this queue again? This queue had row and column. Okay. So I think we can actually just do neighbors I. Right, so now we've pushed the current neighbor, and that's what we're supposed to be doing. Mark discovered at queue. Okay. Done that. Now it's going to go back into this while loop, and the queue, well, after it goes through all neighbors. Okay, so there is one problem here, and that is when we do this, if it gets to the edge here, for example, row -1 is going to be a negative, and when it tries to get the current here, that won't actually exist. So what we're going to do is skip any neighbors that skip any neighbors that are outside the bounds of our 2D grid array. So if n row is less than 0, or n row, so let's say n row is -1, then we don't want it, or n row is greater than, let's see, cells dot length -1, then we don't want it. Continue. Now if, just do the same thing for the columns, if n column is less than 0 or n column is greater than cells n row, right, so this is the individual columns in the row, dot length -1, we are also going to continue. Okay. All right, so now we wrote some code here. Let's actually see, so let's do a little log console.dir here, parent for cell. Let's just see what we got if we do it. So let's click on this, click. All right, so we have something. All right, as you can see, there is data here. So our code is working to generate our parent for cell lookup table. So that's good. All right, so let's just go ahead here and let's see, we're up to here, generate path. So let's just see if we make a path, what happens. Const path. So path would just be a list of all the cells in order going backwards. All right, so generate path with connected cells. Okay. So let's see here. So we have target, which is this. We have row and column passed in. So make sure we don't have any, nope, we're good. Okay. So we want to know what the target is. So let's say target key is going to be row, column. Oops. Row, column. Okay. So now let's see. So while, let's see here. So let the current one we're looking at is going to be target. And so target is cells, row, column. Okay, so target is whatever we clicked on. If we clicked here, for example, then the row column would be, I think, 0 and then 8. So we're going to set that to current. And then start is this guy, and we already pre-store start. So it's this variable, and then we set it here. So we know what start is. Now, if while current not equal to start, so as long as the current cell we're looking at is not equal to the starting cell, we're going to add the key to path. Yes, so we need the key. So that's target key current. Okay, so let's see, path.push. Is that right? If we push we can just push the node, I think. Okay, push current. Okay, so current is target, so we're basically going backwards. So we're pushing, if we clicked here, let's say, we're going to push this node right here onto this path. Now we have our parent for cell lookup table. And so what we're going to do is now set current to parent for cell. Now parent for cell takes in a key, the key being a row by column format. And so that's going to be this target key. So let's change this to let and actually make this current key so it makes more sense. So the current key is when it starts, before we do the while loop, is the row and column that we clicked on. And then the current cell is, of course, cells at the row and column we clicked on. And so what that is, if you recall, we saved two things in here. So current key, we saved key, and then we saved cell. So that's here. That's what that is. So we save that in here by key. So now we're going to use it. So current is going to be cell. Oops. And then current key is going to be key, right? That looks pretty good. So let's see. We start here. Current key is the target cell we clicked on, and the current is the target cell we clicked on. And then while current not equal to start, so that's going to be true to begin here, we're going to push current, which is this, onto our path list. Then we're going to get the parent for this target, which is going to be one of these cells. We're going to set current to that cell, current key to that key. We go back through the while loop. Current, one of these, is still not equal to start. Then we're going to push current onto the path, and then we're going to get that parent, which is one of these. So that looks like it makes sense. All right, so now we're going to have this path. Let's console.log out this path. All right, so let's just click on here, array 8. So in 8 cells, it'll get there, which seems reasonable. All right, those are all rectangles. So now last thing, we are going to change color of all the cells. Okay, path.forEach, loop through all these paths, cells, cell. And then cell.set options fill. So now we're going to want it to be an orange. And let's see, I have this color pre-saved. Let's see. Okay. Let's see what it does. And there it goes. Oh, right. We are ignoring the walls. Yeah, okay. So let's do here. Okay, in this neighbors. So if the neighbor's a wall, we also don't want it. So if grid n column, n row, n column, let's see, wall is equal to 1. Continue. So that should be right. Let's try that again. There we go. So there you see it. Um, that's basically the pathfinding. So now what this does is it's going to look through the entire board before it generates this path. And that's not exactly efficient. So let's just show you how that goes. We have this as an async function. So we're going to slow this algorithm down and let you watch what it does. So let's come down here. So let's see. So we have the current, so we want the neighbor cell, which is I, dot set options. So let's make this blue, red, green, blue. Okay, now we're gonna wait for seconds. So wait for seconds is a utility function that we've created. It's over here. It's nothing more than a promise that resolves after a set timeout. So we're gonna do a wait for seconds, and let's just wait a tenth of a second here. We're gonna set that to blue. And then when we come down here, we're gonna unset it. So when we shift, okay, so if current key is not equal to start key, so we don't want to do this to start. So start should stay red. So if it's anything other than start, so all these other white tiles, we're going to do current dot set options fill. So we're gonna, let's use a light blue. So we've stored a light blue here. Copy. Okay. Okay, let's see. Let's see. Click. Oh, error. Neighbors. Oh no, neighbors is of course a row and column, right? Yes, not neighbors. So we push that, that's good. Cells in row in column. Well, that should not have changed itself, but fix that. Ta-da! So it expanded the entire world or cell or grid that you may have before stopping, even though, well, I guess we picked the edge here. So let's just pick something closer, right? So that was it. And of course it found it. And even though it found it, it's going to do the entire grid before generating that path. So now let's see. Why is it turning it blue? Ah, yes, I guess if the neighbor is the start, it should also ignore. Okay, right. So let's put in parent for cell. We're going to add start. So start key. And then the key, I don't think this actually matters, but we just need to note that we've already checked start. So it has no parent. So now let's try this again. There we go. So now it's not changing our start to blue. Because we can just assume that our start has always already been discovered. Okay, so that was, of course, not very fast. Now we can speed this up without having to check the entire board, even when we've already found the target. So that's actually quite simple. So let's just get here, and then, so we know what the target is, right? Right here, the row column. So if we do target key down here, current key, it doesn't matter. Okay, if current key, so if the current key is equal to, we're going to start key, parent key, let's just make a target key. So target key is going to be row, column, great. So if current key is target key, I'm going to break out of this while loop, right? So that means we've already found it. I think this is right, at least. Let's try it. And it will have found it, and it's done. Now, see, that is much faster. We didn't have to go through the entire board, even though it's already found it. So there's that. Let's just watch this a little bit more. It's kind of cool, right? It's doing the breadth-first search, and then once it finds it, then it draws the path to where it's going to go. And now, so it looks pretty good. So if you had your character and you wanted to get like a point and click game. So you wanted your units or your one unit to go to this area of the map, and they're over here. You would click on it, does this algorithm, then it finds a path. You can just walk to this XY, to this XY, to this XY, etc., until it gets to where it needs to go. So now let's show this to you by adjusting this this world here, so you don't think that we've somehow gamed the system by making this board look a specific way. So let's say we're going to block. Let's just say right this, right? So what does this look like? All right. So now, if it wants to get here, it's going to have to walk around. So let's watch it go. There it goes, and there it is, right? So it's going to walk all the way around to get to there. So now let's say we're getting to here. It's going to do the breadth-first search, and then it's going to find the path. Let's see, what else is interesting? How about this? And found the path. So there we go. So that is breadth-first search, and then using that information to get a path of the tiles or the cells that your character would need to walk across or through to get to the target location. Now, this is not the most optimal algorithm for doing this. A* pathfinding is the more optimal algorithm for this and commonly used in games. So do let me know in the comments below if you'd like to see a video on A* pathfinding. Now, thanks for watching. If you want to see more videos on algorithms and game development, let me know in the comments below and do subscribe.